Okay, so this week we're talking about multiple regression, and we'll basically be replicating the exact models that we fit in SPSS, and we're going to go ahead and estimate them here in R. So, the first thing you want to always do is open up the right projects because it just makes reading and loading data much easier. And it's also useful because it shows you the files and folders and all that. And so you can see how I just did that. I just went up here and whatever it's named on your computer, you're going to go ahead and select it there, and you'll know the project's loaded when you see the project name there. You can also tell because it points you to like the main project folder. So that's actually, this blue cube is actually the R project file. And so on your computer, it'll pop up like that with that little icon. So this week, we're going to be doing the week 4 multiple linear regression code. And so, starting from here at the top, really, really easy to build up to multiple regression in statistical software once you've already done simple linear regression. So, I'm importing my data with the same line of code we've been using in the past. Again, you can click the downward arrow, see your variables there. You can click there too. You can see like the clicker button pops up like that. And you'll see that this shows kind of a nice little data view. So, you can look in Excel or you can look at your data here. And now we're going to go and fit the multiple linear regression model. So the form is you have the linear model function, and that takes a few arguments. So here we've only put 2 arguments at the moment. You can put many more depending on what kind of options you might need. But here I'm specifying the model. So this is model specification. I'm letting the DV be SAT verbal scores. I'm letting that depend on teacher pay, percent taking, and percent no high school. So of course, each of these have the relevant beta, should be beta 2 and beta 3. And really couldn't be easier to specify this thing in R, right? And of course, I need to tell it what is the appropriate data set. So I'm going to run that code, store it in the mod object. You can, of course, print it there. I don't find that very useful. So I tend to prefer to look at the summary. I think most people do in R. And we also talked about an omnibus or overall model significance test. So that omnibus test is actually just when you hit the summary, it actually shows you right here. So SPSS breaks these out into like 3 different tables. R gives you the coefficients table, just like SPSS. And then it just goes ahead and puts on the bottom here, just tacks on the model summary table from SPSS, which is about R squared. So you can see 80.8 or 80.9% of the variation in the DV is explained by the model. You've also got adjusted R squared. Then this is what SPSS calls the standard error of the estimate, which is better called the residual standard error or the standard error of the regression. So the average prediction error is about 15 points. And finally, it gives you the ANOVA and SPSS. It gives you in the ANOVA table, it gives you the omnibus test results. And like I was saying, usually people are just going to look at the p-value there, and you've got the F statistic. It's degrees of freedom. There's 2 degrees of freedom for the F, and it's p-value. So, really pretty easy to fit and interpret your regression models in R. Really comes out the same, kind of just more compact here. Now, there's also an ANOVA function, but if you call that, it actually shows a little bit different than the ANOVA table in SPSS, because this is like the ANOVA table in SPSS, it basically groups the explained sums of squares into like one test. But here you can see it's kind of breaking them out. You got the explained sum of squares due to teacher pay, the explained variation due to percent taking, and the explained variation due to percent no high school. So that's how you can that's how you can think about this ANOVA table, but I wouldn't really worry too much about the ANOVA table because honestly, it's not as useful I prefer to look at the coefficients table, and you see the p-values are similar, 2.8. Yeah, you can see that percent no high school. And so anyways, just use the coefficient table. Don't use the ANOVA. I just wanted to point that out because that is kind of confusing. You can read more about this function online if you want. Now, the other thing that we looked at, actually, I forgot to add something, and that's standardized coefficients. So I'm going to just show you, I don't know how to do this on the top of my head in R. So I'm going to show you how you would actually do this in real time if you needed to use it. So I would come here and I would type in R OLS regression standardized coefficients. And there will be a lot of different things you can click on. Stack Overflow is very helpful. That's usually for answering people's specific questions. But let's see here if one of these has an answer for us. So they're just, yeah, that makes a lot of sense. So look, there's going to be tons of different answers you can use. This is actually something I've used in the past, but there's a scale function, which remember in the lecture on Tuesday, I said there are two ways to get at the standardized coefficients. You can either just z-score everything, which means you take that variable, subtract its mean, divide out its standard deviation. So you center and standardize. And the scale function actually does that. So you're actually z-scoring y and you're z-scoring x here. So I'm going to go ahead and just use this approach. And again, you can look on Google. There's going to be different approaches. You can probably get a package that will actually just estimate it for you. But I prefer, whenever possible, to not use packages. So let me go ahead. And we're going to write out, I need to pause my Dropbox. Okay, so this is, I'm going to write out, get the standardized coefficients. How do we do that? Well, we're just going to we're going to z-score each variable. Actually, let me show you a different way. So I could do it. I'll show you two ways to do this. I could literally scale it like this. And I could fit this model and these estimates should be the same that you get in SPSS. So, this is negative 0.093 for this one. This is negative 0.15 for percent taking and so forth. So, it's putting it out in scientific notation there with the e's, right? But let's say I actually wanted to add standardized variables to my data set, because in this way, if I come here and type in data, oops, that's the wrong data. I need to type in dat. I don't have the z-scored variables in there, but I can actually create them. Let's see, create z-score version of data. So I'm going to z-score the few continuous variables we're using here. So I have dat, and I'm going to create a new column. Verbal is my DV, so I'm just going to add z to it, and that's just going to basically just going to z-scale itself. I'm going to copy that. I've got 4 variables, so I don't want verbal. I want teacher pay here. I want percent taking here. I want high school. And of course, make sure you're keeping that here. And then I'm also going to come and just add z's to the end of all of these. Z, Z, Z. So what this is doing is making a new variable named SAT verbal, and that it's going to store in that new column just the old SAT verbal, but it's going to apply the scale function. And just remember, anytime you're not sure what something does, you can just question mark, type it in, and look, it centers and scales it by dividing by the standard deviation. So you can actually mess with both of those settings. Here it's showing me the default is to center and scale. So if I do this, now look, if I type in, if I look at the summary of my variables, the mean of a z should be about 0, right? Summary of the whole thing. And look, the last variables that it's going to add, I'm not sure why it did that v1. That's weird. Why did it do that? Oh, did I forget? Well, I'm not really sure why it's showing this in the output, but you can see here in my data set that they are not having that v1. I'm not sure what that's about. Yeah, so I honestly don't know. I've never noticed that before. But anyways, if you look at the mean here, you know, you put them on 0. And if you look at the variance, let's just look at the variance of one of them. So I'm going to do the SD, the variance and the standard deviation of the same thing, right? Just the SD, the square root. So I'm going to come down here and look, the SD and variance, you know, square root of 1 is 1. So the Z scoring works just like that, right? It makes the mean and the variance, the mean 0, the variance 1. Okay. So now I have 4 variables. I've Z scored them all. And now I can rerun this whole thing. Comment here, note that the Z score version of our data is not saved. So usually, you know, if you're going to really do analysis on a z-score variable, I would always create it and save it just so that it's in the underlying data set. And now I've got to do capital Z's here. It is case sensitive. And I will get the same answer that I saw earlier. So 4.830. Scroll up. So there you go. So you can see you can do it either way. You can, both approaches are basically doing the same thing. You're standardizing it before you put it in the regression. It's just in the second approach, we're actually saving the standardized variables in new columns in our data set. And I would typically recommend that's the approach you use. So of course, you know, you pick out, this has got the largest standardized coefficient. So we would say this has the largest effect on the DV. Now, the other thing we learned in the lab was how to do incremental tests. And so, you know, I showed you various ways to write the null and alternative hypotheses. I tend to prefer to write the whole model. And I should write error I. There's always error in our models, right? And so you can see here in the null model, I'm comparing a model with just teacher pay to one where I'm actually going to add percent no high school and percent taking to the model. And those are going to be beta 2s and beta 3s, right? So you could also write that as beta 2 and beta 3 are 0 in the null versus at least one of them is not in the alternative. And so now what I'm going to do is I'm going to create 2 different models, and I'm literally calling this mod H0 because this is like my null hypothesis model. And then I've got another one that's mod HA, and you can see the difference is pretty straightforward, right? Just add it to 2 variables. I've stored them in here, and you know, of course, they're going to show up in my environment, and I can start manipulating them and pulling all kinds of stuff out of these data objects. But to do this comparison, it's really easy. I just go ahead and throw them in the ANOVA function, and you should put the smaller model first and the larger model second. And let's say I had like 3 or 4 models I wanted to compare. You could keep adding like mod HA2, mod HA3, or whatever you want to call it, and throw them all in the ANOVA function here, and you would actually get the statistics that you're interested in. And so for model one, we're comparing that to a model with no predictors. It's so not interesting that R really doesn't even show you that, but you can get that in the summary table. The omnibus test is basically what that is. So that's why R doesn't show it there. It's already showed as the omnibus results when you call summary on mod. You'll see it there. So like this command would show you the F statistic and whether it's significant at the bottom. So we don't need that though. We only need the second row of data, which is comparing model HA to model HO. And so, it's the same result as we saw in the lab. It is statistically significant. So we conclude that the model HA here is preferred to H0. And I also put here how you could report that in the text of a journal article. Now, that's what we did in lab. I also provided, I'm going to actually have to update this because I think the data set was not importing. So I'll update this and upload it on Canvas. But one of the things I said in the lecture was that you can also think about can we get equations for these things? Because when we did simple linear regression, we literally had an equation for B and A, for alpha and beta, right? The estimates of alpha and beta. We could write it down, we could compute it, and it is kind of useful to learn that. We lose our ability to do that in multiple regressions, so we have to start using linear algebra. And so that's basically like, also called matrix algebra. And so, if you execute this code, basically it shows you that how do you actually do that? I think it's kind of interesting and kind of crazy that you can just multiply a couple matrices together and stuff, and you actually just get out the estimates of the slopes as well as their standard errors. It's kind of crazy to me, honestly. So I'll let you go through this on your own. I'm just gonna have to change the example because I think this was not reading in data. It wasn't doing it correctly, at least. Yeah, see, it's one variable, not gonna work. So I'll fix this and post it to Canvas. And of course, if you have any questions, let me know. Happy to talk with you guys about anything you're curious about. So that's all for today. And thanks for listening.